Hello class, Mr. Anderson here. The purpose of this video is to provide you with step-by-step workthrough of the calculations required to complete a recent assignment. And that assignment has to do with the line emission spectrum for hydrogen. So I have displayed through the projector on the board here the line emission spectrum for hydrogen. I realize it's probably difficult to see, but you probably recall that when we saw the line emission spectrum for hydrogen, there were 4 distinct lines of color that you could see. So starting over here, we have a violet color that was difficult to see, that has a wavelength of 410 nanometers. There's a second blue line with a wavelength of 435 nanometers, a third sort of teal color, blue-green color, that has a wavelength of 486 nanometers, and then finally a fourth line that is red in color that has a wavelength of 656 nanometers. Your assignment was to do 3 steps in your calculation. Step 1 is to convert from nanometers to meters. Step 2 is to calculate the frequency of each wavelength of light. So you'll do it for each of the 4 wavelengths. Step 3 is then to calculate an energy for each wavelength. Alright, so let's begin. We'll start with the first wavelength, or the violet color light, which has a wavelength of 410 nanometers. And we'll go through each of those 3 steps. Step 1, convert nanometers to meters. Step 2, calculate the frequency of this light. And thirdly, calculate the energy that a photon of this light has. Okay, let me just cover up the screen, or the projector, so we can see the board better now. Alright, so step 1, convert nanometers to meters. The wavelength of light that we're working with is 410 nanometers. So this is a conversion problem. We're going to use the conversion skills, right, that we have to convert nanometers to meters. We are given the equivalence between meters. 1 meter is 1 times 10 to the 9, or 1 billion nanometers. Remember, nanometers are really, really tiny unit of distance. So as with any conversion, we start with the quantity that we're given. In this case, 410 nanometers. You recall that in our conversion process, we just put this over 1. That's simply to set this up in fraction form. We will be multiplying this by a conversion factor that is also in fraction form. The conversion factor is going to come from this information. Again, 1 meter is equal to 1 times 10 to the 9 nanometers. So the conversion factor, we need to figure out what's on top and what's on bottom. The trick to that is that we need to cancel nanometers. So we recall, in order to cancel nanometers, it needs to be on bottom in our conversion factor. So I'll put 1 times 10 to the 9 nanometers on bottom, and that is equivalent to 1 meters, which I can put on top. Just looking at the units, not doing the numbers. With the nanometers in the numerator and the nanometers in the denominator, those cancel, we can cross them out. The unit that is left is meters. I'll go ahead and write that in our answer space. Now we're left with just the numbers, and you may use a calculator to help you do this. You have 410. You're going to multiply that by 1. So that's obviously 410. Then you need to divide by what's on bottom, which is 1 times 10 to the 9, or 1 billion. So 410 divided by 1 billion. When you complete that calculation, you'll end up with 4.1 times 10 to the minus 7 meters. And that's a small number, 4.1 times 10 to the minus 7. If you think about it, that makes sense. In order to have 1 meter, we need to have 1 billion nanometers. With 410 nanometers, we're not even close to 1 billion. So we end up with a very small number when we're in the unit of meters. Okay, so that's step one. That's step one. You've converted your wavelength of light from nanometers to meters. Great. Now we'll move on to step 2. Sticking with this wavelength of light, right? Step 2, we want to calculate the frequency. So calculate the frequency that corresponds to 410 nanometers. To do that, we're going to use the speed of light equation, right, which we know is c, the speed of light, is equal to lambda times nu, where lambda is your wavelength and nu is your frequency. Speed of light is a constant that's given to you. Speed of light is equal to 3.0 times 10 to the 8 meters per second. Okay? So if we're trying to solve for frequency, right, we want to rearrange this equation so that we can solve for frequency, so that it's all by itself. Right now, because it's being multiplied by lambda, we need to divide each side by lambda. That cancels lambda on this side, and we can see that frequency is equal to the speed of light divided by lambda, the wavelength. Now, all we need to do is plug in those values. The speed of light is given to us as 3.0 times 10 to the 8 meters per second. That goes on top. On bottom, in your denominator, we have the wavelength, right? And in step 1, we converted wavelengths to meters, and that's the way we need to use it here, right? So our wavelength is 4.1 times 10 to the minus 7 meters. The reason we had to do step 1 is to plug it into this equation. You'll notice that the speed of light is meters per second. Our wavelength has to be in meters as well in order to cancel that unit. We could not have left it in nanometers, and otherwise it would not have canceled. Right? So looking at units before we go to the numbers, we can cancel our meters. The unit that is left is 1 over seconds. Now that's kind of a strange unit, but that is the unit of frequency. Remember, frequency is the number of times that a wavelength goes by per second. Right? So 1 over seconds is a good unit for frequency. Now again, you can use your calculator to help you complete this calculation. You're dividing the speed of light, 3.0 times 10 to the 8, divided by 4.1 times 10 to the minus 7. When you complete that, you'll get a number of 7.3 times 10 to the 14. That is a large number, right? And that makes sense. That is wavelength with a small, or light with a small wavelength like that has a very high frequency. Okay? So that's your answer to step 2. Calculate the frequency. Third step is we need to calculate the energy. Calculate the energy that a photon of this wavelength of light has. For that, we're going to use the formula E equals H times nu. E stands for energy. H is a constant called Planck's constant. We'll be given that value. And nu is our frequency. And in step 2, we just calculated the frequency of light that we're using. So all we need to do is plug in our frequency value, multiply it by Planck's constant, and that gives us the energy. Planck's constant has a value. It's on our board here. It's 6.626 times 10 to the minus 34. Very, very small number. And it also has kind of a strange unit. It is joules, which is a unit of energy, times, I'm going to use a little dot to represent a multiplication, right, times seconds. Again, a strange unit, but it's a constant. It is what we call a complex unit because we have a unit of energy combined with a unit of time, right? But again, you don't need to memorize this. This is a constant that will be given to you, right? We just need to use it. All right, so let's pause for a moment, and then I'll come back with the completed calculation.